Hi everyone, in this video I'm continuing to take a look at question 7a of the 4-unit HSC exam from the year 2000. I've already worked through part 1 and 2 in prior videos, so have a look at those if you haven't already. Here we're looking at part 3, which says, by considering part 2 with equal values of yi for I is equal to 1, 2 and so on up to n, prove that the maximum value of the sum from I is equal to 1 to n of xi log 1 on xi is log of n. And the conditions are where the sum from I equals 1 to n of xi is equal to 1, and xi is positive or greater than 0 for I is equal to 1, 2, and so on up to n. So let's take a look. I've written up basically what we're dealing with. So very similar to part 2, you can kind of see how this leads on from part 2. The only missing ingredient really is there's no yi here where there was before, we've just got a 1. But basically we want to show that this sum is maximized at log n, and we've got some conditions. And we're basically given a hint, we're dealing with equal values of yi. So I think where in part 2, the essence was how do we define x to get something useful. I think here in part 3, it's how do we define yi to get something useful. And again, in an exam environment, you might find yourself having to do a bit of trial and error, trying things and seeing what works. Here, I think if we let yi equal 1 on n, I think we're going to get somewhere helpful. So, again, given we're following on from part 2, and part 2 was all about what's yi on xi, I think if we're going to define yi as 1 on n, then it makes sense to think about, well, what's yi on xi going to be, and then see how we can then plug things into our result from part 2 to try and get this result in part 3. So yi on xi would be basically yi, which is 1 on n, times 1 over xi is basically it. So therefore, what we can say is from part 2, we can take our inequality that we showed. So we can say that the sum from I is equal to 1 to n, so the sum from I is equal to 1 to n of xi times the log, so xi times the log of yi on xi, but we've just shown that that's going to be 1 on n times 1 on xi. So we know the log of that is less than or equal to 0. That's exactly what we showed in part 2. Now here we can use some of our rules of logs. So we can say, therefore, the sum from I is equal to 1 to n of xi times, and we can break these logs apart. So the log of something times something else is just the log of that something plus the log of that something else. So going right back to logarithm basics there. So that's going to be less than or equal to 0. And we can break out this summation now. So we can say, therefore, the sum from I is equal to 1 to n of xi log 1 on n plus the sum from I is equal to 1 to n of xi log 1 on xi. That's all going to be less than or equal to 0. Now, this log 1 on n, maybe if I just kind of over to the side here, again, we're going back to basics on our log rules, but the log of 1 on n, that's basically the log of n to the negative 1, because 1 on n is just n to the negative 1. And as we know with logs, what's up here in the exponent we can bring to the front. So that's just negative natural log of n. So let's put that in. So we can say, therefore, this bit here, well, this log of 1 on n, we can just say is negative log of n. I might just bring the negative out the front. So that's negative sum from I is equal to 1 to n of xi log n, and then plus what we've got left. So the sum from I is equal to 1 to n of xi log 1 on xi, and that's all less than or equal to 0. Now we're looking good here because this bit that we've got here is exactly what we're focused on. So it's really about, well, what's the deal with the rest of it here? Now, remember that the sum from I is equal to 1 of xi, we're told that one of our conditions is that that's going to be 1. And log of n, the natural log of n, has nothing to do with I in here. So actually, we can say that this negative sum from I is equal to 1 of xi log n, that's really just negative log of n, which we can bring out because it's got nothing to do with I, times the sum from I is equal to 1 to n of xi, which we're saying is 1 in terms of getting to our result, so times 1, plus the sum from I is equal to 1 to n of xi log of 1 on xi. That's all less than or equal to 0, but now we can bring out log n over. So we can say, therefore, the sum from I is equal to 1 to n of xi log of 1 on xi will be less than or equal to, and the negative log n just comes over as positive log n. So there you have it. I mean, we've got this left-hand side is always going to be equal to the log of n. So if it's always less than or equal to that, and we've got equality at some point, then that's the max. So we can say, therefore, this kind of, I guess, identity or this summation, this sum from I is equal to 1 to n of xi log of 1 on xi is maximized at log of n. And I think that's pretty much it. That's all there is to that question. So, I mean, I think the key to it is almost very similar to the key to part 2. How do we define yi so that we end up with something useful? I think getting the yi as 1 on n, I mean, if you didn't start there and you tried something else, like if you said, well, what if I let yi equal to 1, for example, you might think, well, over here in part 2, I had log of yi on xi, and here I have log of 1 on xi, so why not let yi equal 1? I mean, you could try that. You'd probably work your way through and not get anywhere. And then you'd think, well, I need to try something else. And I think how you kind of get to 1 on n being useful is because you know that you're dealing with an inequality with 0 in part 2, and that's where we're going to start. And we need a kind of negative that we can bring over. We know that thing that we want to bring over will end up as log n, and you kind of then got to have almost the mathematical imagination to go, well, this is going to get me there, this log of 1 on n. And how do I get a log of 1 on n? Well, if I make yi 1 on n, I kind of get there through my log rules. So it's almost reverse engineering what you need yi to be based on where you want to end up. And that's going to take a bit of creativity, maybe a bit of trial and error in the context of an exam, but hopefully you get there within the time limits that you've got. I think a real difficult part of a lot of these exams is the fact you're doing this under time pressure. And as you get towards the end, so back in 2000, there's 8 questions on this exam, you kind of know that question 6, question 7, question 8, they're kind of going to start throwing curveballs at you. And so the real trick is not necessarily the complexity of the mathematics. The algebra here is not beyond any 4-unit student, really. It's can you kind of work out what's going on with the question and kind of get to the heart of what the question writer is wanting you to do. And I think that's where all the difficulty lies. And sometimes that can take time. And I think for a lot of 4-unit students, it's probably just that they run out of time. Anyway, hopefully for this part 3, what I've done here makes sense and you can get your head around it. What I'll do now is I'll in the next video, take a look at the final part 4 of this question, and that'll wrap it up. All right, tick boom.